Hello, ladies and gentlemen. Today I'm going to discuss a compressible flow question with using ANSYS software. The problem in hand is a 9 mm bullet fired from a Glock 17. We will test the flow over that bullet. After I finish the sketches on a SolidWorks software, I I start the ANSYS software application through Workbench. Um, First, we drag the fluid flow fluent from the left side, and first thing we will do, we will import the geometry. Browse and bullet. Then we will open this geometry, and we will press generate. Okay, now that we have the geometry, a schematic of the geometry, the first thing we will do, we will go to tools and enclosure and make an enclosure. The cushion would be uniform, and the dimension would be 0.2 meter, um, and that is because the whole dimension of the bullet is 9 mm, so 0.2 millimeter is even too much. We will generate again. We will have two bodies. We will rename them bullet surrounding. Generate one more time, and then we can close. We will have a green tick. Discard the mesh. Wait for it to open. Okay, the purpose of the surrounding is to make a whole system for the flow as if it's in real life. We'll go to the geometry. Um, Double check the bullet surrounding, they're available. Then we will rename the outlet and inlet. This is the outlet, and the inlet will be the other side around. This is the inlet. Both are in the X direction. Okay. Knowing that ANSYS is a calculator and it can only solve with some criteria, so for ANSYS to be able to calculate the pressure, temperature, and velocity distribution over the bullet, we have to reduce the elemental size to increase the number of elements and to prevent diverging fluid. We will go to mesh, change the relevance to 15, and that will increase the fineness. If it is the negative, if it is, for example, negative 15, that means that the flow is rough, or the system will be in a rough course. Not sure why it's not writing negative. Negative, yeah, you're negative. But in our case, it should be positive. Then we will go to sizing. The size function should be proximity and curvature. This will assure that the um, mesh will be constant at uniform areas while increasing the mesh at curved areas or decreasing the elemental size. The relevance should be fine, not coarse medium. This means rough. Smoothing should be high as well. All of these are based on trial and error. So it depends, every system has its own criteria. The minimum size of each element should be my case 0.001 and the max phase size 0.0085. If it's 0.001, 0.0001, the mesh will be obsolete. Okay, there is nothing else to do here. So we can go and generate mesh. Take some time, not too much. Okay, now we have the mesh. We can show the cross section across the bullet. Mesh down. Okay, here is the meshing for the bullet. That's it. And also we can determine the number of elements. It is 325,000 and something. Okay, now that we're done with the meshing, we can close it and press update. Make sure that you have the green tick before completing the next step. Otherwise, the whole system will not function. Okay, we have the green tick and go to setup. Okay, in the setup area, because either you can use serial, which takes a lot of time, or parallel, but using the parallel, you have to know the number of logical processors you have in your computer, and try not to use all of them. Otherwise, if the system crashed, the whole computer can crash, and whatever is done will be lost. Okay. Pressure base is for compressible. Density base is for compressible fluid. My condition is density base, compressible fluid. We will check. Done. Model. Viscous laminar. Spa Almarat. In viscous laminar, Spa Almarat and K epsilon are for turbulent. The rest are not recommended. Spa Almaras uses one equation, while K epsilon uses two equations. For simplicity, we'll use Spa Almaras. Material, ideal gas, in the density field. Solid aluminum, and make sure to press change grade. Double check. Okay, cell zone boundary condition. Okay, in the boundary condition, the inlet should be pressure far field. The gauge pressure should be 101,325. Check the sea level pressure, atmospheric pressure. The max number should be 1.1, and that is based on the Glock 17. Temperature 288 atmospheric. Outlet should be pressure outlet. There's no need to change anything with that. Reference value, compute from inlet, and the surrounding will be the reference zone. Solution, yeah, monitor. We should add two graphs, drag, surrounding, plot, right, and it is in the x direction, and lift, plot, right, wall surrounding, lift in the y direction. Uh, okay. Solution initialization, initialize, hybrid initialization. We will do 10 steps. Make sure that the system is okay, done. And this is a condition if you think that your computer can crash or anything, if you want to auto save, but you will not need it hopefully. Check in case. These are the recommendations by ANSYS. You don't have to go with them. Um, Number of iteration 500 for my system. That's enough based on trial and error at least. That will take time. I'll pause here and come back once that calculation is done. Okay, welcome back. The calculation is complete now. This is the CL conversions and CD conversion. It's almost straight line, so we can say that it converged while the CL needs more iteration. But the 500 iteration took 15 minutes, and I think we don't need more than that. Now we close the uh, setup and we go to results. Okay, we have the green tick again, results. We'll create a contour, pressure, contact region will be this, and number of contours around 1500. Okay, this is a problem with the software. I'm not sure why, but when I do the other contour, first I'll do the plane about the XY there, and we can notice it here. It's cutting through and cutting through the bullet. And create another contour. Close the first one. Where did it go? Yeah, contour, pressure, 1500. Contact region will be the plane. And apply. Yeah, we can notice the shockwave about the pressure. Temperature variation, still contouring. Okay, this took around 20 seconds. This is the temperature variation, and even zoom in. And for the velocity, it is. Here is the velocity. Okay, now I'll show the pressure variation across the first contour. Just have to close the plane. And this is about the bullet itself. You can see that the pressure is at the maximum at the tip, and it varies throughout. We can also show the constant pressure plot diagram and calculate it.